Hi, this is Mr. Broyles from Silver High School, and today I'm doing video 2 on forces, which is our second unit. And what we've been doing is the standards we've been using are the science and engineering practice of using math and computational thinking, and the cross-cutting concept, the CCC, of cause and effect. So yesterday, or in the last video, we looked at describing what causes a force, and if you remember right, what causes a force is a push or a pull or anything that changes the motion. We talked about the elementary forces, and with the elementary forces we looked at there's gravity, the electromagnetic force, the weak nuclear force, and the strong nuclear force. And then we also looked at the units of force, newtons and pounds, and we converted between them. And we said that newtons, that there in 1 pound there was 4.448 newtons. All right, so today, let me go back here. Today I want to talk about deciding if a force is a vector quantity or a scalar quantity and why that is. List the types of forces and describe their uses, and then learn how to calculate weight. So if we move forward here, for a vector quantity or a scalar quantity. Well, force is a vector because if we remember from past discussions, vectors have magnitude and direction, and scalars just have the magnitude. So for a vector, for force, I've got 40 newtons in a direction. It could be north, south, east, west. It could be plus or minus. So I've got forward, backward. So one of the things we need to do is we need to learn to draw some diagrams to help us see what's happening. And that's what we're going to be doing some today, is drawing these diagrams. So what I'm going to go back to my document camera, and we've got a problem we've got a picture to draw. So a 15 Newton force is placed on a box that moves it forward. That moves the box forward. Draw the situation. All right, so when we're drawing this, we need to think about, all right, what's our direction and how are we going to show the direction? Well, the direction is forward. So we need to define what forward is. So we're going to say that forward is in that direction. So what I'm going to do is I'm going to draw a box, and since I'm pushing it, I'm going to put my force here, and this is going to be 15 newtons. Now, because I've described forward as moving to the right, when I draw my arrow to the right, that says that it's 15 newtons moving forward. And we tend to think of forward as in the positive direction, so I could also write it as 15 newtons forward with a plus sign there. So now what I want to do is I want to talk about the types of forces. And there are 2 types of forces. There are contact forces and there are field forces. Contact forces are where the objects have to touch each other. And this we think of as tension, pulling on a rope, pushing something, pulling something, a spring, and the spring is attached to something because the spring compresses and it elongates, and it does this. And then there are field forces. Field forces affect objects without touching them. And here we have gravity. Gravity is caused by mass, and it pulls objects toward the center of mass. And then the electromagnetic force is a force that causes the interaction of the positive and negative charges or poles of an object. So they don't have to touch. I can hold a magnet up and I can pull something or push something that is metal along. So they don't have to touch. So contact forces have to touch. Field forces act without touching. And then now I want to talk about mass and weight. And we're going to calculate weight here when we're done. So there's a difference between mass and weight. Mass is the amount of stuff in an object. Weight is the pull of gravity on that object. So let's think about this. Where do we have more weight? On the surface of the moon or on the surface of Earth? So we need to think, which is more massive, moon or Earth? Earth is more massive, so there's more gravity that's going to be generated there because there's more mass. And so Earth is going to have a higher weight for you on the surface of Earth than if you're on the surface of the moon. Matter of fact, the moon is about 1/6 the gravity of Earth. So now I want to look at some calculations. So, of course, there we go. All right, so the first calculation I want to look at is I want to calculate the weight of a 60 kilogram person in newtons. And I want to do it on Mars, and I want to do it on Earth. Now, Earth has an acceleration of 9.8 meters per second squared, and Mars has a g of 3.7, and we have newtons per kilogram. Now, I'm going to show you down here that a newton per kilogram is the same thing as a meter per second squared. Because if you remember from the last video when we were talking about newtons, we said that a newton was a kilogram meter per second squared. So if I do kilogram meter per second squared, because that's my newton, divided by kilograms, I have a division problem here, and I have two improper fractions. So what I'm going to do is I'm going to change it from a division to a multiplication, so I have 1 over kilograms. So my kilograms cancel, and I'm left with meters per second squared. So a kilogram or a newton per kilogram is the same as meters per second squared. So What I know is I know that weight equals mass times g, the acceleration due to gravity. So if you remember, we can use our math triangle here, and we can say that weight is equal to mass times gravity. So we can set our triangle up like that. So if we're solving for weight, we cover up weight, we have mg, we're going to multiply. If we're solving for mass, we're going to cover up m, and we've got w divided by g. And then if we're solving for g, the acceleration due to gravity, we're going to do weight divided by mass. Newtons divided by kilograms. So for the weight on Mars, I'm going to have 60 kilograms. I've written my formula down. So I'm going to fill in my formula. My mass is right here, 60 kilograms. And my acceleration due to gravity here is 3.7 newtons per kilogram. This is this right here. All right, so now I have 60 times 3.7. So 60 times 3.7 in my calculator, and I get 222 newtons. Now, I'm going to do my acceleration on Earth. So I know I've got weight equals mass times gravity, and I know that my mass is 60 kilograms because I have the same person. I'm just moving them now to Earth. So 9.8 meters per second squared. So what I end up with is 60 times 9.8, and I get 588 newtons. So there's my acceleration on Mars. There's my acceleration on Earth. All right, this is the end of this video, and I will see you in the next video. Have a good day.